Hello, welcome to the EPG Pathshala. In this module, we will study the potentiometry. The potentiometric methods involve the measurement of the potential of electrochemical cells in the absence of appreciable currents. And the basic components are reference electrode, glass which gives reference for potential measurements, indicator electrode where species of interests are measured, and potential for measuring the device. An electrochemical cell is set up which can be discussed as in this module. In this module of potentiometry, we will study what is potentiometry, why is it required, where it is used, how it is used, and how it is used in real life, and what is its importance. Potentiometry is a classical analytical technique with roots before the 20th century. It is based on the measurement of potential of an electrode system. In the presence of multitude of other substances, it enables the selective detection of ions. It is one of the electrochemical analytical methods. An electric circuit is used to measure the current and potential created by the flow of charged particles. For complete electrochemical cell from which the negligible current is drawn, the EMF is given by E cell is equal to E indicator minus E reference plus EJ. E indicator, E reference, and EJ are the potential of the indicator electrode, reference electrode, and liquid junction potential respectively. The potentiometric methods cover two major types of an analysis. One is direct measurement, which involves the direct measurement of an electrode potential from which the activity of an active ion may be derived. Other kind is indirect potentiometric method, which measures the variation in EMF brought by the addition of a titrant of the sample. The basic setup of potentiometer is shown in the figure. During the discharge transfer process, it follows as movement of electrons from zinc electrode to copper electrode. In the solution, zinc ions move away from the electrode and sulfate ions move towards positive ions move towards right and negative towards left in the salt bridge. On the passage of electrodes, electrons are transferred to ions. Zinc dissolves and metallic copper deposits. The basic fundamentals of potentiometry are: the electrode potential is developed and is given by the Nernst equation whenever metal ion is immersed in a solution containing its own ions Mn positive. E is equal to E naught plus RT over Nf log A Mn positive. The value of an electrode potential E can be established by linking the calomel electrode and measuring the EMF of the resultant cell. It can be deduced from the reference electrode. It is also possible to measure the potential directly via direct potentiometer. This involves the use of an electrode of second kind, for example, silver chloride electrode formed by coating a silver wire with silver chloride. This measures the concentration of chloride ion in the solution. The basic functions of potentiometer are as: step 1, to measure the electric potential or voltage. Step 2, by rotating the potentiometer wheel, we are changing the voltage applied to the resistor, which results in more or less light coming out from the light emitting diode. To control electrical devices such as volume control on equipment. It works as a rheostat and provides varying resistance depending on the flow. Furthermore, the requirement and methodologies used to accomplish the analysis are modified day to day by the researchers working in this field to improve the routine analytical methods. The equipment required for direct potentiometric measurements includes an ion selective electrode, a reference electrode, and a potential measuring device. The reference electrode should provide a highly stable potential for an extended period of time. The ion selective electrode is an indicator electrode capable of selectively measuring the activity of a particular ionic species. Ion selective electrodes are mainly membrane-sized based devices consisting of selective ion conducting materials which separate the sample from the inside of the electrode. It is necessary to select an appropriate electrode, both indicator and reference, depending on chemically reacting components in various titrations. Reference electrode is the electrode with a potential which is an independent concentration and temperature. It must be reversible and obeys the Nernst equation. It gives the stable potential with time and always returns to its original position after the passage. The common reference electrode used in potentiometer is calomel electrode, mercury of Hg2Cl2 saturated and KCl mixture, and the half reaction can be shown as a mercurous chloride plus 2 electron forms 2 mercury plus 2 chloride in a reversible reaction. A reference electrode E reference is a half cell having a known potential that remains constant at constant temperature and independent of the composition of the analyte solution. Another is an indicator electrode having a potential that varies with variations in the concentration of an analyte. Metallic indicator electrode and membrane electrodes are types of indicator electrodes. Metallic indicator electrode. Metallic indicators are classified further into the electrode of first kind, electrodes of second kind, and an inert redox electrode. First kind is a pure electrode that is direct equilibrium with its cations in the solution. The equilibrium between the metal and a cation is shown as Xn positive aqueous plus N electron forms X solid, for which E indicator is equal to E naught plus 0.0592 over N log AX N positive, where indicator is the indicator electrode potential of metal electrode and AXN positive is the activity of the ion. The metallic indicators are not very selective and respond only to their own cations, due to which these are not widely used for the potentiometric determinations. For example, copper electrode cannot be used for the determination of copper 2 in presence of silver 1 because electrode potential is also a function of the silver ion concentration. Similarly, many electrodes are there which cannot be used for the determination purpose. Electrodes of the second kind respond to the activity of ions that form sparingly soluble precipitates or stable complexes with such cations. The potential of a silver electrode can be written as silver chloride solid plus electron forms silver solid plus chloride aqueous, for which the Nernst equation is E indicator is equal to E naught silver chloride silver minus 0.0591 log activity of chloride ion concentration, activity of chloride. Thus, silver chloride can serve as an indicator electrode of the second kind for the chloride ion. Note that the sign of the logarithmic term for an electrode of this kind is opposite to that for an electrode of the first kind. Potentiometric titrations. The measurement of an analyte can be done by the titration, in which the potential of an indicator is measured as a function of the volume of titrant added. This is known as potentiometric titration. Sudden changes in the potential of EMF against volume of titrating solution reveals the endpoint. A typical potentiometric curve is shown. Neutralization titrations. Neutralization titrations are performed with standard solutions of strong acids or strong bases. A standard solution is a reagent of exactly known concentration. These are useful where visual endpoint detection is not permitted by the presence of colored species or turbidity. The strength of an acid and base will depict the equivalence point. The standard solution used in this titration. Two basic methods are used to determine the concentration of standard solutions. One is direct method. A carefully weighed quantity of a primary standard is dissolved and diluted to an exactly known volume in a volumetric flask. In the second method, the solution is standardized by titrating a weighed quantity of a primary and secondary standard. The hydronium ion concentrations are widely different for various indicators. For example, phenolphthalein indicator works in the range 8.3 to 10, methyl red 4.0 to 6.3, methyl orange 3.1 to 4.4, bromothymol blue works in 6.0 to 7.6. Another titrations are precipitation titrations. These titrations are based upon the formation of a highly soluble or slightly soluble precipitate termed as precipitation titrations. This titration is very important because it is perfect method for the determination of halogens and metal ions. The magnitude of change in potential at the equivalence point depends on solubility of the substance being precipitated. The titration curve is influenced by Ksp value. When the value of solubility product constant is small, the titration curve is perfect. The indicator used in titration of chloride ion is chromate ion, in which the endpoint is being signaled by the appearance of red silver chromate, and it can be represented as shown in the equation. The potassium nitrate salt bridge is introduced between the sample solution and saturated calomel electrode so that potassium chloride does not diffuse into the sample. Complexometric titrations. The formation of complex results from the interaction of sparingly soluble precipitate with excess of reagent. For example, when silver nitrate is treated with potassium cyanide, the initially produced silver cyanide dissolves in excess of potassium cyanide. The reaction continues till all the cyanide ions have been converted into complex ion. The increase in concentration means the gradual increase in free silver ions. It leads to increase in potential, which determines the equivalence point. But if addition continues even after this point, EMF changes very slowly and silver cyanide is precipitated. Differential titrations. In order to increase the accuracy attainable in the titration of acids and bases, it is desirable to have precise methods for evaluating the purity of the several substances that are commonly employed as acidimetric and alkalimetric standards. The technique requires two identical electrodes, one of which is well shielded from the bulk of the solution and the other is contained inside arm test tube. Due to the restricted access by the addition of a titrant, the composition around the shielded electrode hardly alters. The small difference in solution composition gives rise to potential difference between the electrodes. At the end point, the value of potential difference is maximum. The elimination of reference electrode and salt bridge makes it more fruitful titration. Automatic titrations. The automatic titrator is provided with 2-point auto calibration and standardization. The instrument is capable of displaying pH and millivolt of the sample with temperature compensation. The automatic titrator can accept a variety of electrodes to cater to provide to various applications in different fields. This kind of instrumentation is ideal for performing the multiple analysis in which the fundamental analytical procedures remains fixed as in quality control situation. The entire titration can be performed automatically by the titrators equipped with microcomputers, digital converters, and using dedicated software. Real-time applications. Potentiometry represents a powerful technique with different applications in biology, physics, as well as in chemistry. It was also used for the respiratory gas analysis in the hospitals, consisting of respired gas samples from the patients undergoing anesthesia. It can also be used for the genomic studies with potential applications for clinical medicine. Due to its speed and sensitivity, potentiometry has played a very important role in space-related applications, drug discovery, geologic research for petroleum composition measurements, carbon dating, and some other research endeavors. Three most interesting uses of potentiometry in real life are: number one, food industry. Titration is a method or the process of determining the concentration of a dissolved substance in terms of the smallest amount of a reagent of known concentration required to bring about a given effect in reaction with a known volume of the test solution. Paper manufacturing. Atmospheric emissions from the pulp and paper manufacturing industries can be determined. Pharmaceutical industries to determine the pH of given chemical agents, and also in the detection of endpoints in potentiometry titrations of certain drugs like amoxicillin, propanadol, etc. We can conclude that potentiometry is a classical analytical technique based on the measurement of potential of an electrode system in the presence of multitude of other substances. It enables the selective detection of ions. An electric circuit is used to measure the current and potential created by the flow of charged particles. In potentiometry, the different titrations can be carried out. There is no need of indicator, and the titrations can be performed even in various turbid solutions. The wide applications of potentiometry makes it a suitable analytical technique for the titration methods as compared to conventional titration methods. We can conclude that potentiometry is a classical analytical technique based on the measurement of potential of an electrode system in the presence of multitude of other substances. It enables the selective detection of ions. An electric circuit is used to measure the current and potential created by the flow of charged particles. Potentiometric titrations of different types are very useful for the titration of analyzing in very complex solutions. Potentiometric titrations are used without the help of any indicator. So potentiometric titrations and potentiometry are a very useful substitute for the conventional titrametric methods. Thank you.